All right, and welcome back. So hopefully at this point you have been paying attention to the lectures in class on series circuits, and you've watched the previous videos on series circuits, and you have a good handle on those at this point and know how to work those problems. So we are going to transition now to the different, or another type of circuit. It's actually the other type of circuit, and that is parallel circuits. And we need to define some rules for parallel circuits. And so first and foremost, we need to define what a parallel circuit is, and we're going to diagram it out to begin with, and then we'll kind of talk through it. So let's represent our battery here. Let's say it has something like 12 volts. And let's give some conductors here. Let's just put 2 resistors in this circuit. I'm going to draw the other resistor right here, kind of bridging between the 2 original conductors. And so here we have a pretty simple parallel circuit, right? And just to kind of remind everyone, E is the variable that we use for voltage. I is the variable that we use for current. R is the variable that we are going to use for resistance. And finally, P is the variable that we use for power. So with series circuits, we defined a series circuit as a circuit only having one path of current flow. Here we can see that there are not just one path for current to flow, but we have multiple, right? And so if we have current coming out of here, I'm trying to do this in a different color, it's going to hit this this T right here. And so we can't put all of it this way and all of it this way. There's a finite amount of electrons flowing per second, and so they have to separate at this T. Some of those are going to travel this way, and some of those are going to continue on and hit R2. Okay, and then once it leaves R2, they're going to come back around to the second T and join up with the electrons that kind of took a left here or went up on the first T. And then once it joins back up, everything comes back together and collects back and goes back into the battery. And so we have a couple instances of current flowing here, and we can start to define those current flows. If we remember back to series circuits, we saw that this one path of current flow, that's all the current we had. Everything that was coming out of the battery went through R2, everything that came out of R2 went into R1, and then everything that came out of R1 went back into the battery, so that's all the current we had. It was only one place for it to go, and we called that IT because that's all the current we had. That was the total current. In this case, we don't have that because we have multiple paths for current to flow. However, we still have IT, but not everywhere. So all the current that comes out of the battery, that's going to be all the current we have to give, or that the circuit has to give. And so we can define this current right here as IT, and that's just this arrow right here, okay? And hopefully intuitively we can see that whatever comes out of the battery has to go back into the battery, and so this also up here is going to be IT. Now, at this junction right here, the current is going to split, and some of it's going to go through R1 and some of it's going to go through R2. And so the current that flows through R1, we will just call that I1, and then the current that flows through I2, we'll just call that I2. And I'll name it I2 here, and we'll also call it I2 here because obviously it continues on. And so now if we look at this section right here, and we can also see it in this section right here, there's a rule, actually a law, called Kirchhoff's current law. And it says that if we treat this as, they call it a node, so this would be a node, and we don't really use this all that much. Whatever comes into the node must flow out of the node, right, to keep it balanced. And so what we have flowing into this node is IT, and what we have flowing out of the node is I1 and I2. And so, therefore, our first rule for series circuits, so rules for, and I think I said series circuit, I meant parallel circuit. Our first rule for parallel circuits is that IT is going to equal I1 plus I2, and if we have a third one, it's going to be plus I3, so on and so forth, for however many resistors we have in the parallel circuit. And we can see that that differs almost exactly opposite that of the series circuit. So in series circuit, it was IT equals I1 equals I2, but in parallel circuits, they're additive, kind of like voltage in series circuits, right? Now to voltage, let's kind of segue to that one real quick. So voltage, again, ET is going to be whatever the applied voltage is, or the battery voltage. And if we look at this conductor right here, okay, remember we talked about having points of potential. I'll go back to this little drawing right here. Remember, this is all one point of potential, and we called it E sub A. Everything over here was one point of potential. We called it E sub B. And then this was one point of potential. We called it E sub C. So everything that is this little area right here within this conductor, we can treat as one point of potential. Now that one point of potential in a parallel circuit is actually contained everywhere there is a conductor, without crossing over any resistor, right? So we can even cross over the node right there because it's electrically the same. It's connected right here. We have no voltage drop in this area. We would have one across the resistor, but not in this area. And then there's a separate node, or I'm sorry, not node, but a point of potential right here, so that this is all the same. So we could call this point of potential up here, now this is E sub A, and this is E sub B. And look there, now we only have 2 points of potential because everything on this side of the circuit is connected and everything on this side of the circuit is connected. And if this is ET, well, let's just take a measurement from right here. Let's say these are multimeter leads, right? We got red and black multimeter leads. Let's place the red on the positive side, the black on the negative side. And if we were to read across the battery, what do you think we would read? Well, we would read this 12 volts of input voltage, right? Well, now let's slide down and read across R1. Well, R1, since this is all the same point of potential up here, and this is all the same point of potential right here, we're going to read the exact same thing that we read over here, because the difference between them is still 12. If we go EA, which is positive 12, minus 0, because remember, negative is always the 0 point of potential, we're going to get 12. And the same thing happens if we come over here and read R2. And in fact, if we read like this, we would also get 12 volts. We would also get 12 volts, okay? And so the voltage across the battery is going to be equal to the voltage across R1 is going to be equal to the voltage across R2. And so that leads us to our second rule, where ET is equal to E sub 1 is equal to E sub 2 is equal to E sub 3, so on and so forth, for however many resistors we have in the circuit. And if we look back on the series circuit, we see that it's the exact opposite. So in series, voltage added, right? So we took E1 plus E2, but in parallel, they're all the same, right? So voltage is constant in a parallel circuit, and current is constant in a series circuit. Those are two really important rules that will come in handy later on. Now, power, if we look at power, that's probably the easiest to remember because it just so happens that it's exactly the same rule for series. So if we're looking at the total power dissipated by the circuit, it's going to be the power dissipated by the first resistor plus the power dissipated by the second resistor plus the power dissipated by the third resistor, so on and so forth, for however many resistors we have in the circuit. And so those are exactly the same regardless of the type of circuit, so it makes it kind of easy to remember. Resistance is where it gets a little tricky, and it's not so much tricky as it is kind of difficult to remember the equation. All right, so let me just write down the equation and try not to freak out. But the equation for finding resistance in a series circuit is going to be 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance for however many resistors we have, and we could continue this on if we had 4, 5, 6 resistors. We would just keep adding them. We're going to take the sum of all of that, and then we're going to divide that into 1. Okay, so essentially we're taking the reciprocal. If you remember from high school or some lower level maths, that this is just the reciprocal. So we're going to take the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3, add all of those together, hit the equal sign, and then take the reciprocal of that value, and that's going to give us RT. Oddly enough, if we have resistors that are of the same value, let's assume that R1 and R2 are both 10 ohms, okay? Then what we'll find is that RT, so we'll say or RT is equal to the resistance value of one of those, right? So let's just use the ohm symbol to show that, divided by the number of resistors. And I'll give you an example of that. So in this case, let's assume R1 is equal to R2, and they're both 10 ohms. And so our example there, so for example, we assume that R1 is equal to R2 is equal to 10 ohms. And so all I'm saying there is that R1 and R2 are both equal to each other, and they're both equal to 10 ohms. Well, how many resistors do I have? Well, I have 2 resistors. And so RT for this case is going to be 10 ohms divided by the number of resistors, which is 2, in which case RT would be 5 ohms. And that's really important to remember. That can speed up calculations quite a bit. Punching this into the calculator, I mean, that's a lot of keystrokes to try to get that into the calculator, and if you miss one, well, you're not going to get the right answer, and you have to have done enough of them to recognize that you don't have the right answer. One thing of note, when doing resistance or total resistance for a parallel circuit, RT will always be less than the lowest resistor. Okay, so we can use this to check our work. If we, let's say the lowest resistor is, let's say R2, and R2 is 5 ohms, then we should be getting a resistance RT that is less than 5 ohms. All right, so again, super important to remember this, and super important to remember this trick right here. If we don't have a situation where all the resistors have the same value, then we have to use this guy right here. And we should be getting a value that is lower than the lowest individual resistor within the circuit. All right. All right, we'll stop the video here and pick it up in just a minute, working out some problems.